guys, so here we're going to talk about the last topic in the chemistry curriculum. It's actually one of my favorite topics. It's called the Chatelier's principle. Now you're only watching this video if you were not in class to see the little seesaw thing. If you don't know what I'm talking about with the seesaw, that means you're okay. Go ahead and keep watching this video. But if you were in class that day, move on to the next video. You'll need your notes and the worksheet on the Chatelier's principle, which is probably in your packet. And this is kind of what it looks like. So if you don't have that worksheet, just go ahead and just kind of quickly jot this down, get this down to make sure that you have it, because that's what we're going to be doing this entire video. So we're going to be filling out the worksheet on Le Chatelier's principle and determine how the equilibrium shifts when we remove some reactants or products, or if we add some, and what happens to the K value. So here we have a reaction. This is actually part of the Haber process. Haber process means that we're taking nitrogen from the air and hydrogen from the air to produce ammonia. And ammonia is super important when it comes to fertilizing all of our farms. So this process was actually really important to be able to add more fertilizers from gaseous nitrogen and gaseous hydrogen. So the first thing we have to do is balance this chemical equation. So here, go ahead through. You should see that we end up having 3H2 and 2NH3. We also see 22.0 kilocalories in the products, and don't forget that means energy. So if energy is in the products, that means that heat is being released, and it's an exothermic reaction. So I want to make sure that you see that in there. That's going to be super important when we're talking about this stuff. So here we have that same reaction. It's all balanced, it's all good to go. And here we have a balance beam. So think back when you were in elementary school. Not a balance beam, a seesaw. So when you're back in elementary school, if there was one side that had a lot more mass, that side went down, the other side with less mass went up. So this is just kind of going to be shifting all around. So let's take a look about what happens if we add N2. So N2 is in the reactants. If we add N2, we end up seeing that the equilibrium will shift, and then eventually the left-hand side goes down. The right-hand side is favored. So the equilibrium shift is towards the right. Overall, that means that you end up having more products being formed. Well, that makes sense, because if you have more reactants, that means you're going to create more products at the end. So the concentration of N2, we can just kind of keep constant. The concentration of H2, you should see that that has gone down, because if this were the level line, the concentration of H2 has gone down. The concentration of NH3 has gone up, and overall for K it stays the same. Don't forget, K only changes if we change the temperature. It doesn't change if we change the concentration. Alright, so that's for the first one. Let's set it back up to normal. There we go. Alright, so again, basic conditions. Now, this next one, we end up adding H2. So H2 is in the reactants. It wobbles for a bit, and then you'll eventually see that H2, or the reactant side, goes down, meaning the products are going to be favored. It's going to shift towards the right. The amount of N2 decreases, the amount of NH3 increases. The K value will end up staying the same because we haven't adjusted the temperature. Okay, let's set it back up to normal, and let's see what the next condition is. Let's see, the next condition is if we add NH3. So NH3 is going to be in the products. So if we add a little bit more of that, it's going to wibble wobble, and then we see that NH3, or excuse me, the right-hand side goes down. The left-hand side goes up, so the left-hand side is favored. It's going to shift, or the equilibrium is going to shift towards the left, meaning you're going to have an increase in N2, an increase of H2. And your K will still be the same because temperature hasn't changed. Alright, let's set it back up to normal. Let's see what the next condition is. Oh, if we removed N2, so we got rid of some N2, and we'll find out that the left-hand side gets favored, so the equilibrium shifts towards the left. The amount of hydrogen goes up, the amount of NH3 goes down, and of course K does not change. Let's reset it. And here, if we remove H2, so I got rid of an H2, it wibble wobbles, and you'll find that it favors, or it's shifted towards the left, so the left-hand side, or the reactants, are favored. You increase the amount of N2 and decrease the amount of NH3. K does not change. So we reset it. Here we removed some NH3. So we got rid of some NH3, and we see that the right-hand side goes up, so the right-hand side is favored. Equilibrium shifts towards the right, and you end up, the amount of N2 and H2 end up, decreasing. Sorry. The amount of N2 and H2 end up decreasing. Of course, K stays the same. And let's kind of go back to that. I want to show you why. If we removed some NH3, we need to make sure that the amount of NH3 goes constant. So we'll take some N2 and H2 and end up making more NH3, so it balances out eventually. Okay, so that's why all this stuff kind of changes. So we reset it. Here we're going to increase the temperature. So the heat is on the right-hand side. We're adding heat into here. So instead of 22 kilocalories, I made it 44 kilocalories. I doubled it. So the right-hand side goes down, the left-hand side is favored. So the amount of N2 and H2 increase, the amount of NH3 decreases. Now here, K can actually change because the temperature is changing. So don't forget, K is actually equal to the concentration of the products over the concentration of the reactants. So let's see what happens here. We added more reactants, so the reactants end up increasing, meaning the products decreased. So we have a lower amount in the numerator, a larger amount in the denominator, so that ends up showing that K will decrease. So K goes down because we have more reactants. If that confuses you, pretend as if it were 1-to-1 initially, and then when we changed it, so sorry, K was 1-to-1. I'm just putting in numbers here just to kind of show it. Here I'm going to show that we end up having less of the product, so I'm going to do it by 0.5, and instead the K is going to be 2. So 1/2 divided by 2 will end up being 0.25. And again, I'm just throwing random numbers in here to show that, hey, the products went down, the reactants went up. And I just used the numbers 1 initially just because they're easy numbers. So the initial conditions were, which are on the left, K was equal to 1. When I changed stuff up, K was equal to 0.25. So that shows you that K ends up decreasing. All right, let's reset it. And let's change the conditions. We decrease the temperature. So right now I have 22.0 kilocalories. Now I'm going to make it by half, 11 kilocalories. So you'll see the products end up being favored. It shifts towards the right. So you end up having less amount of N2, less amount of H2, and more NH3. So let's figure out what ends up happening to K. So initially we could have had 1/1, products over reactants to 1/1. Now I'm changing it, so I can increase the amount of the products, or excuse me, yep, the amount of products, so the top number increases, but I'll decrease the amount of the reactants. So when we have this, K is equal to 4. So initially, K was equal to 1. When we decrease the temperature, K was equal to 4. So K ends up increasing. Right, we'll reset it. Here we're going to talk about pressure. So if we increase the pressure, and this is going back to the gas laws, so pressure goes up, that means the volume goes down. That's a super important key concept to remember. They're inversely proportional to one another. So if we increase the pressure, that means that's going to favor the side with the least number of moles. The reason for that is because if the volume decreases, there's not enough space for the side that has the most amount of moles. So you're going to favor the side with the least number of moles. And of course, this is just dealing with gases. If you have anything with solids, liquids, or aqueous, then pressure does not affect it. This is only for gases. So let's take a look. Over on the left-hand side, we had 1 mole of N2, 3 moles of H2, so there were 4 moles of gases in the products, or excuse me, in the reactants. And in the products, there were only 2 moles of gases. So we're going to, if we increase the pressure, the volume goes down, we're going to favor the side with the least number of moles. Hence, we're going to favor the product side because it only has 2 moles, whereas the reactant side had 4 moles. So we decrease the amount of N2, decrease the amount of H2, increase the amount of NH3. And K doesn't change. So we're going to reset it. We decrease the pressure. So if we decrease the pressure, that means that the volume increases. So if the P goes down, the volume increases, and this time we favor the side with the most amount of moles, hence the reactants. So your N2 and your H2 increase, the amount of NH3 will decrease. Alright, so to quickly summarize, temperature is the only thing that affects the K value, and you can add or remove reactants or products to determine that equilibrium shift as well. Before that balance beam, I forgot to mention this to you earlier, pretend it's your pencil. Like if you add some more reactants to one side, you kind of weigh that side down, the other side goes up. So just kind of play around with doing that. Alright kiddos, I will see you later. Take care.